Jain to all. Today I am here to present the second lecture of the lecture series for subject digital signal processing. The topic of this lecture is designing of IIR digital Chebyshev filter, and I am Dr. Amit, associate professor in EC department of AKGEC. Okay, so start with the all pole analog filter. So why we have started with all pole analog filters? Because the filter, Chebyshev filter, which we are going to see, is an all pole filter. All pole filters are those filters in which there is no zeros present. Okay, or you can say in the numerator part of the transfer function, the value is constant. Okay, so so if we'll discuss about this all pole analog filter, so most important low pass filter in this category are Butterworth and Chebyshev filter. There are two types of Chebyshev filters. One is Chebyshev type 1 filter, another one is Chebyshev type 2 filter. So if we'll see, then Chebyshev type 1 filter is an all pole analog filter. Okay, and if we'll see the transfer function of all pole analog filters, all these filters are described by this general transfer function, which is having the form of HAS equals to A dash upon PS, where PS represents some polynomial in S, and A dash is basically gain. A dash is basically a constant, and if we want to design these filter or realize these filter, then we can realize these filters in their cascaded form. Okay, so if you want to implement it in cascade form, so the transfer function can usually be written in these two forms, and these two forms are dependent upon the order of the filter, whether the order of the filter is odd or whether the order of the filter is even. That is dependent upon this. Okay, so if the filter order n is even, then we will use this general formula. HAS equals to multiplication k equals to 1 to n by 2 bk ohm c square upon s square bk ohm cs plus ck ohm c square, where n, which is filter order, is value is having 2, 4, 6 or any n and any even number value. Okay, and so like if we'll take as an example, let's say n equals to 2, so our transfer function HAS will become, from here if you will see, you will write here k equals to 1 to 2 by 2, it means k equals to 1 to 1. It means the transfer function is simply b1 ohm c square upon s square plus b1 ohm cs plus c1 ohm c square. Okay, so this is the transfer function this is the transfer function which we will use when n equals to 2. And here we want to design the IIR digital filter, but IIR digital filters are well approximated by their analog counterpart. So what we will do, we will first design the analog filter, which is our HS, and then we will convert this HS, which is the analog filter transfer function, into digital one with the help of the transformation available. Means we are having transformation wherein we can convert analog filter transfer function into digital filter transfer function, and there are two methods for this. One, you know, that is basically the IIT method or impulse invariant transformation method, and second one is BLT or bilinear transformation method. Okay, so this is the formula for n equals to even, for n even, where n value is from 2, 4, 6 up to so n, and this formula which we can see here is for n odd, where n is starting from 1, 3, 5, 7. Okay, so if n equals to 1, then we will have this only this value. Okay, your transfer function is b0 ohm c upon s plus c0 ohm c. But what happened if n equals to 3? So if n equals to 3 and you will put this value over here, so it will become k equals to 1 to 1. So you are having the value, if you will write transfer function for n equals to 3, then in that case you are having transfer function b0 ohm c upon s plus c0 ohm c, and from here you will get b1 ohm c square upon s square plus B1 ohm CS plus C1 ohm C square. Okay, so this is the transfer function. So our aim is to find out basically the order of the system, order of the transfer function or order of the filter. Once we get to know the order of the filter, then according to the order of the filter, whether the order is even or odd, we will find out the respective transfer function corresponding to an analog filter. Okay, so you can see these are the this is the transfer for an analog filter where n equals to 3. Okay, now if we will see, if we will go through the design, then we will find that there are some things that we have to calculate. What are those values? If you will see, we have to find out these capital BK value, small bk value, small ck value, filter order n, and here you can see omega c, large omega c, which is the cutoff frequency. So if we all know, if we know these things, if these 5 parameters, then we can find out the transfer function for any analog filter. Okay. Now come to this thing we will see later on. First we will see this Chebyshev filter. About Chebyshev filter, what is this Chebyshev filter? So Chebyshev filter, the magnitude response of a low pass Chebyshev filter is given by mod of h j omega equals to a upon 1 plus epsilon square cn square omega by omega c whole power 0.5. So this Cn, what is this Cnx? Cnx is the Chebyshev polynomial. Cnx is the Chebyshev polynomial. Omega c is the 3 dB cutoff frequency. Epsilon is the constant. Okay, and so now how we will define this Chebyshev polynomial? So you can see here the magnitude response of Chebyshev filter is dependent upon A. Generally the value of A, highest value of magnitude, we will assume it as 1. And epsilon is a constant, and another thing that we have to calculate is Cnx, which is this Chebyshev polynomial, where x, we can say, if we are assuming that omega by omega c is x, so we have to calculate the value of Cnx. So once we will calculate, and this value of Cnx is dependent upon the value of n. So again the factor of n came into the picture. Okay. So now how we will explain this Cnx? So Cnx can be simply represented by Cnx equals to cos of n cos inverse x. This is the case when mod x is less than or equal to 1. Okay, but if mod x is greater than 1, then in that case the formula that we will use for calculating the Chebyshev polynomial is cos of n cos hyperbolic inverse x for mod x greater than n. And this we can simply write another form of this formula is cos hyperbolic n log x plus under root x square minus 1. Okay, so the magnitude response, if you will see from this curve, is that you can see here, this is the pass band. Here in the pass band we are having the equiripple width. We are having the equiripple pass band. You can see the width is equal. Okay, that's why we are having ripples which are of equal length. Okay, and here you can see the pass band is flat. So you can say in Chebyshev filter or Chebyshev type 1 filter, in the magnitude response, the pass band is equiripple, pass band is having equiripples, and stop band is maximally flat stop band. Okay, and another important thing is that you can see here n1 is greater than less than n2, the curve is like this, n2 is less than n3, curve is like this, and n3 is the highest value. Okay, so you can see as you will increase the order of the filter, then what happened, the magnitude response of the filter approaches towards ideal filter response. Okay, so if you will increase the order of the filter, then what happened, the response approaches to ideal filter response. It means the transition bandwidth is getting narrower and narrower. Okay, and if we will discuss about the phase response while increasing the order n, so if you will increase the order n, then the phase response of Chebyshev filter will become non-linear and non-linear. Okay, it means as you will increase the order, then non-linearity will increase. And if we will talk about the comparison between Butterworth and Chebyshev filter, so for same filter order, let's say n equals to 5. So we will see the magnitude response is more sharper in case of Chebyshev filter, but if we'll see the phase response, then the phase response of Chebyshev filter is more nonlinear as compared to Butterworth filter. Okay. Then, so this I have already discussed. So you can calculate the Chebyshev polynomial values, like if you want to calculate C0x, you can easily calculate C1x, you can easily calculate. Okay, how you will calculate? Let's say mod x is less than equal to 1 and you are calculating the value of C0x. So then what happens? C0x will become cos 0, that will become 1. If you want to calculate C1x, so n equals to 1, so it means cos of cos inverse x. It means you are getting the value x. Similarly, you can calculate the values like C3x, C4x. Okay, but what happened when the value of n is higher? Let's say n equals to 5. Then it is very difficult to calculate the value of C5x using those formulas. So for that, for the convenience purpose, there is some recurrence formula which is given to you. So this formula says that if you want to calculate the value of, let's say, C5x, then the value of C5x can be calculated by 2x C4x minus C3x. So now you know these values, or you can, if you don't know C4x, then again you can put C4x value here, and C4x is dependent upon 2x C3x minus C2x, like this. Okay. So there are some properties of Chebyshev polynomial. These are properties. Mod of Cnx should be less than equal to 1 for all mod x less than 1. Cn1 equals to 1 for all n. And all the roots of polynomial Cnx occur in the interval -1 to 1. And mod of Cnx increases monotonically for mod x greater than 1. So from here you can see that let's say this is the cutoff frequency, and you can see as soon as the cutoff frequency passes, so what happened? The value of this term will become greater than 1, and if it is greater than 1, then we will use this cos hyperbolic formula, and according to this formula, your magnitude response will suddenly decreases. Okay. So now here we have calculated the values of like C0x, C1x that I have already told you. So like initially we are taking the case where omega is between 0 and 1, and we are calculating the value of Cn omega. So that will become Cn omega will become cos n cos inverse omega. And how we will solve it? Let us suppose cos inverse omega equals to theta. So omega equals to cos theta. Okay, so we will write it like C n omega will become n cos theta, n cos inverse cos theta, and it will become cos of n theta. Now, once you are having the value of Cn omega equals to cos of n theta, you will simply put n equals to 0. When you will put n equals to 0, then it means C0 omega will become cos 0, that will become 1. And for n equals to 1, this value will become omega. And for n equals to 2, this value become 2 omega square minus 1. And for C3 omega, this value will become 4 omega cube minus omega. And similarly, if you calculate C4 omega, C4 omega will become cos 4 theta. Cos 4 theta can be written as 2 cos 2 theta square minus 1. And you know the value of cos 2 theta. You have already calculated here. C2 omega, that will become 2 omega square minus 1. So when you will solve it, you are having this value. Okay. So similarly, you can compute the higher order polynomials for n equals to 5 and 6. But it is difficult to solve it using this formula. So we will use this recurrence formula for calculating this. Okay. So this is the case when omega is lying in between 0 and 1. Another case is that when omega is greater than 1. So in that case, Cn omega will become cos hyperbolic on n cos hyperbolic inverse omega. Let's say cos hyperbolic inverse omega we are taking as y. So this will become cos of hyperbolic y. Okay, so omega will become cos of hyperbolic y, which we can write as e to the power y plus e to the power minus y upon 2. Now, we are assuming that y is far greater than 1. If y is far greater than 1, then e to the power minus y can be neglected. So if we are neglecting this, then you can say cos hyperbolic y is equivalent to e to the power y by 2. Or you can write it simply e to the power y equals to 2 omega. Okay, now we will take natural logarithmic on both sides. So we are having y, log ln of e to the power y is y, and ln to omega. Okay, so this is this, and this y is also from here will become cos hyperbolic inverse omega. Okay, so therefore Cn omega will become cos hyperbolic, and cos hyperbolic, and in place of y you will write L log 2 omega. Okay, uh, and then you will put the expansion of it, and finally you are having Cn omega will become e to the power log 2 omega to the power n plus e to the power minus log 2 omega to the power n upon 2. Now, because our omega is greater than 1, then Cn omega will become e to the power log 2 omega to the power n by 2. We are neglecting this term again. So we are having Cn omega equals to 1 by 2, 2 omega to the power n. So this is the final result which we are getting for Cn omega when omega is greater than 1 is 1 by 2, 2 omega to the power n. Now what we will do, we will simply put the values. Let's say for n equals to 0, we will calculate the value, it is 1 by 2. For n equals to 1, it is omega, then 2 omega square, then 4 omega cube. So this is how we will calculate the values when omega is greater than 1. Now design parameters for low pass filter with the desired specification can easily be seen here. This delta 1 is pass band ripple. Okay, and this omega 1 is pass band H frequency, this delta 2 is stop band ripple, this omega 2 is stop band H frequency. Okay, now what we will do, because we know mod of H e to the power j omega in case of Chebyshev filter is represented by this expression. So and here we will put the value of a equal to 1. So we will use this expression over here. So we are having this equation number 4 and equation number 5. Okay, now for designing constraint, for making design simple, what we are doing, we are assuming that the cutoff frequency of this filter is equal to the pass band H frequency. It means Cn omega c by omega c you can write, and it is Cn1, and the value of Cn1 equals to 1. So therefore equation 4 in this case can be written as delta 1 square is less than equal to 1 upon 1 plus epsilon square, because the value of this term will become 1 when omega c equals to omega 1. Okay, so this is one parameter epsilon we can easily calculate from here, and now again solving it, we are getting the epsilon value in terms of delta 1 square. Now order of the filter can again be calculated by again assuming that omega 1 equals to omega c using the equation 4, and this we can obtain as, if you will solve it, you are getting this n will be greater than equal to cos hyperbolic inverse 1 upon epsilon multiply 1 upon delta 2 square minus 1 to the power 0.5 upon cos hyperbolic inverse omega 2 by omega 1. This you can easily calculate. Okay, and now we are having the value of epsilon here, we are having the value of formula for order n here, we are having the value of delta 1 and delta 2, we are having the value of omega 1 and omega 2. This is small omega, we can calculate the large omega value by using the transformation that was specified. Okay, and another thing is that like we are having these parameter coefficient values. So these are small bk, small ck and capital Bk formulas. So these are the design formulas. Bk is dependent upon Bk formula is 2yn sine 2k minus 1 pi by 2n, where yn is the one of the expression which is like this, which is dependent upon epsilon and n. So first what we will do, first we will calculate n, first we will calculate omega 1, omega 2, then we will calculate n. Once n is calculated, then you will calculate epsilon, then you will calculate, first you will calculate bk, you will calculate, before bk you have to calculate yn, yn once you will calculate, then you will calculate bk, then you will calculate ck, and then last you will calculate bk, because in the formula of bk a small ck will be there. So this is the way you are calculating the parameter values. Okay, once you will calculate all these values, you will be able to find out the required transfer function for the filter. So let us see one numerical based on this. Design a digital Chebyshev filter to satisfy the constraints. These are the constraints given for digital Chebyshev filter. So here in this question, this is given as passband ripple, which is known as delta 1, and this is stop band ripple, which is called as delta 2. Okay, and this is passband H frequency, this is 0.2 pi, and this is stop band H frequency. So now this is basically a low pass filter. It is not mentioned over here that this is a low pass filter, but you can see this is a low pass filter because the magnitude of pass band is higher. So this is the specification of pass band, and so that's why this is pass band H frequency. And in case of low pass filter, the pass band H frequency is always less than stop band H frequency. That's why this value is higher, and this corresponds to stop band. This corresponds to stop band, and also in stop band, in low pass filter, the magnitude value is very low. Okay. So we have calculated delta 1, delta 2, 0.2 pi, omega 1, omega 2. Now, first we will design analog filter. So corresponding to analog filter, we should have large omega 1 and large omega 2. So you know, because in this question it is mentioned that you have to use bilinear transformation. So in case of bilinear transformation, it is omega equals to 2 by t tan omega by 2. So accordingly, we will calculate omega 1, that will become 2 by t tan omega 1 by 2. Then you will put the value of omega 1 over here. So you are getting this value. Okay. So we know in case of Chebyshev filter, we have already taken the approximation that the cutoff frequency is equal to passband H frequency. So that's why this is the same value we can use for cutoff frequency of this filter. Okay. Then we will calculate omega 2. Omega 2 is 2 by t tan omega 2 by 2, and omega 2 is 0.5 pi. And when you will solve it, you are getting the value omega 2, that will become 2. One important thing that you have to keep in your mind is that while calculating all these values, your calculator must be in radian modes. Okay. If it will be in degree mode, then all the calculation will become wrong. Okay. So now, because in our order formula, what we have to use the ratio of omega 2 and omega 1. So it is better to calculate the value of omega 2 by omega 1 first. So the value of omega 2 by omega 1 from here will become 3.0779. Okay. Now what we will do? We will determine the order of the filter. Okay. So now how we will determine the order of the filter? The formula you know is n is greater than equal to cos hyperbolic inverse 1 upon epsilon multiplied by 1 upon delta 2 square minus 1 to the power 0.5 upon cos hyperbolic inverse omega 2 by omega 1. So you can see that in the order formula, epsilon term will be there. So first you will calculate the epsilon value, and epsilon formula is 1 upon delta 1 square minus 1 to the power 0.5. 1 upon delta 1 square minus 1 to the power 0.5. Okay, so now the value of delta 1 you can see from here, it is 0.707. So you will just put the value 0.707 here. So it will become 1 upon 0.707 whole square minus 1 to whole power 0.5. So when you will calculate it, the best way of calculating is, like you know, the value of 0.707 is nothing but 1 by root 2. Okay, so it is 1 by root 2 square. It means 2 will be in the numerator and 2 minus 1 will become 1. So this is the value of epsilon, which we have calculated as 1. Now in this formula, we will put the value of epsilon as 1, and we will put the value of delta 2 also, and also omega 2 upon omega 1 we have already calculated. This is 3.0779. Okay, so this is very important aspect that how you are calculating this value of n. So the value of n will become 1.669. As you know, the value of n should be an integer value, so we will choose the next value, that is equal to n equals to 2. Okay. So now based on value n equals to 2, we will determine the filter transfer function. So you know, for a second order, when n equals to 2, this will become the transfer function, general transfer function, b1 ohm c square upon s square plus b1 ohm c s plus c1 ohm c square. Okay, now we know ohm c. Now we will calculate capital B1 small C1. Okay. So first of all, for calculating any of these, we have to calculate yn, which means y2. So y2 is dependent upon filter order n and epsilon. You know both. You will calculate, you will put this value of epsilon and n over here to get the value of y2, which is equal to 0.455. Okay. Then you will calculate the value b1. b1 is will become 2y2 sine 2k minus 1 pi by 2n. So you will get the value 0.6435. And similarly, you will calculate the value of c1, which is equal to yn square plus cos square 2k minus 1 pi by 2n. This is 0.707. Now with the help of this expression where a equals to 1, we will put the value of c1 over here, and because n equals to 2, so it will become b1 by c1, and this is 1. So, and we will put the value of epsilon. So we will finally get the value of b1 as 0.5. Now we will put all these values in the system function hs. So we are having system function hs. So this is the transfer function of an analog Chebyshev filter. Okay. Now because after simplification we are having this transfer function. Now you know, because digital filter transfer function can be obtained using bilinear transformation by putting s equals to 2 by t z minus 1 upon z plus 1. So you will simply put s equals to 2 by t z minus 1 upon z plus 1 in this expression. Okay. The value of t is given as 1, and you will easily put the value of s over here. So you have put the value of s as 2 by t z minus 1 upon z plus 1. And finally, when you have solved and rearranged, the final transfer function will become hz equals to 0.0411 1 plus z to the power minus 1 whole square upon 1 minus 1.4418 z to the power minus 1 plus 0.6743 z to the power minus 2. It is important that your transfer function must be given in negative powers of z, and also in the denominator part the coefficient should be 1. One coefficient should be 1, because this we have already seen in the case of realization structure. Okay. So if you will represent the transfer function in this form, then it will become correct. Okay. So this is the reference I have taken. Okay. Thank you.